Einstein's Field Equations, the Inside Story, Episode 2, The Architects of General Theory of Relativity. Very warm welcome to this very new special episode on understanding Einstein's field equations. In this video, we are going to explore the architects or the creators of general relativity. As history accounts that it was not Einstein alone who completed this magnum opus. There were many friends, mathematicians, and specialists who contributed to this extraordinary work. As you can see that with Einstein there was a general shift on the idea and thoughts, and he worked upon many mathematics and physicists' formulas and concepts, and that is why we call standing on the shoulder of giants. The development of Einstein's ideas were a shift into differential geometry, what is called Riemannian geometry, tensor calculus, and also parallel transport. Taken everything together, Einstein would have been standing on the shoulder of enormous giants who contributed, mentored, and philosophically laid the foundations of the creation of the general theory of relativity. Marcel Grossman, son of the manager of a textile factory, Marcel Grossman was born on the 9th of April 1878 in Budapest. Einstein's friendship with Grossman began with their school days in Zurich. Grossman was an expert in differential geometry and tensor calculus, just the mathematical tools providing a proper mathematical framework which Einstein needed for his work in gravity. Known for his metric components as a tensor, Marcel Grossman did a significant contribution. He introduced Riemannian tensor, then unknown to Albert Einstein, and the general notion of vector calculus. Grossman, you have to help me, or else I will just grow crazy. This was a comment which was made by Albert Einstein to Marcel Grossman. It was Grossman who emphasized the importance of non-Euclidean geometry called Riemannian geometry, also known as elliptic geometry, to Einstein, which was a necessary step in the development of Einstein's general theory. The fact that the metric components are components of a tensor is to be attributed only to Grossman. It was he who realized that a branch of mathematics had developed in which the Gaussian theory of surfaces featured only as a special example. Famously, Grossman alerted Einstein to the existence of the so-called absolute differential calculus, which has been presented in a comprehensive joint paper by Gregorio, Riccicurbastro, and Tulio, Levi, Civita, which we will see in this video. Grossman introduced Einstein to the absolute differential calculus, started by Christoffel and fully developed by Ricci and Levi Civita. This is an extract from the notebook where it is shown that Grossman introduced Einstein to the concept of Riemannian tensor. Grossman facilitated Einstein's mathematical journey towards the general relativity. Grossman, who helped in numerous occasions developing Einstein's idea on differential geometry, Riemannian and curved surfaces, died of multiple sclerosis in the year 1936. Tulio Levi Civita, born on the 29th of March 1873 in Italy. Attending his schools in Padua, Levi Civita showed his extraordinary ability in mathematics. He is famous for his work on tensor calculus and its application to the theory of relativity. He also made significant contribution in other areas. At the University of Padua, he studied under Gregorio riccicurbastro. In 1900, he and riccicurbastro published the theory which Albert Einstein used to resource to master his tensor calculus, a critical tool in the development of the general theory. Tensor calculus helps to develop independent theories which doesn't depend upon the choice of coordinates. Levi-Civita symbol, another key ingredient of general relativity, and Levi-Civita connection. In 1917, he introduced the notion of parallel transport in Riemannian geometry, very important, which motivated by the will to simplify the computation of the curvature of a Riemannian manifold. Levi-Civita's series of papers on the problems of a static gravitational field were also discussed in his 1915 to 1917 correspondence with Einstein. As you can see, we generally denote the Greek symbol epsilon as a Levi-Civita tensor. In other conventions where epsilon is not a tensor, it is referred to just as a Levi-Civita symbol. You must note that Levi-Civita tensor is an isotropic and a rank 3 pseudotensor. That means it is not a pure tensor, but it acts more or less like a tensor. And that is why epsilon subscript ijk is not a tensor, as it doesn't change under coordinate transformation. So people who are listening to this who are not mathematically that inclined can just skip this part of the video, as we will be explaining in a much more lucid manner what this Levi-Civita tensor actually means. Tulio Levi-Civita carefully read Einstein's 1914 papers and attacked Einstein's theory. He objected to the major problematic element in Einstein's theory, which reflected to its global problem. Its field equations were restricted to an adapted coordinate system. The major problematic element was Einstein's theorem and its proof, and Einstein's belief that if the coordinate system was an adapted coordinate system, then the gravitational tensor is a covariant tensor. Wrong. Einstein proved that his gravitational tensor was a covariant tensor for adapted coordinate systems. In an exchange of letters and postcards that began in March 1915 and ended in May 1915, Levi-Civita presented his objections to Einstein's above proof. Einstein tried to find ways to save his proof, but he found it hard to give it up. Finally, Levi-Civita convinced Einstein about a fault in his arguments. Levi-Civita methodically kept all Einstein's replies to him. It is evident from this that after numerous exchange of letters, the two men had grown to each other a sufficient respect. In one of the letters regarding Levi-Civita's new work, Einstein wrote, "I admire the elegance of your method of computation. It must be nice to ride through those fields upon the horse of true mathematics, while the like of us have to make our way laboriously on the foot." Gregorio Riccicurbastro, born on 12th of January 1853 in Italy. His work is instrumental in the development of absolute differential calculus, formerly also called the Ricci calculus, but now known as tensor analysis. He is known for Ricci curvature, Ricci tensor, Ricci flow, each of these elements featuring in Einstein's field equations. As you can see in this picture, I have highlighted the R, which is a Ricci curvature tensor, the first one, and Ricci scalar, the next one. They are important and crucial in Einstein's mathematical formulations. By 1900, Ricci had developed his famed theory of tensor calculus, an extension of vector calculus to tensor fields. He would continue to expand the theory with the help of one of his students, Tulio Levi-Civita. The theory later enabled Albert Einstein to develop his theory of relativity. Einstein even traveled to Padua in 1921 to meet Ricci. As you can see, I have mathematically explained Einstein's usage of Ricci's method, the Ricci scalar marked by R and Ricci tensor. G mu nu equals to R mu nu minus half of G mu nu R. Here G is the Einstein's tensor, R is the Ricci tensor. So this Einstein tensor is symmetric, which means G mu nu is equal to G nu mu. So whatever the way you write it is the same. Einstein tensor allows to write the field equations in much more shorter way. Again, to those who are not mathematically inclined or not sound, you can skip this part because I will be explaining it to you in a much more easier fashion. Albert Einstein found Ricci's methods to be indispensable in the mathematical formations of his general relativity. In applying tensor analysis to the study of surfaces, Ricci encountered several interesting metric properties of hyperspaces. One of them was the Ricci tensor, which occurs in Einstein's gravitational equations and is often called Einstein tensor. Well, what can you tell about this man? Born in the kingdom of Prussia, David Hilbert is one of the most influential mathematicians ever lived. Known for Hilbert's axioms, Hilbert's problems, Einstein-Hilbert action, and Hilbert space, he has been a key element in the arena of mathematics. Einstein presented his field equations on November 25, 1915, but 6 days earlier, on November 20, Hilbert had arrived the identical field equation for which Einstein had been searching for such a long time. It is from here the controversy starts whether it was Hilbert or Einstein who submitted the theory. In 1915, Einstein visited Hilbert in Göttingen, and Hilbert convinced him that the goal of a fully general relativistic theory was achievable, something Einstein had nearly convinced himself that it could not be done. Einstein returned to work, and by November he had found the field equations which gave general relativity its final form. However, Hilbert also worked on the ideas of Einstein, which he had discussed with him, and published a paper how Einstein's theory fitted with his own ideas on the role of mathematics and physics. On November 7, 1915, Einstein wrote David Hilbert and sent him the proofs of the November 4 paper. I am sending you the correction to a paper in which I change the gravitational equations. Einstein told Hilbert that he had corrected his 1914 review paper and into the paper of November 4 after I myself realized, Einstein writes, about 4 weeks ago that my previous method of proof was fallacious, since Hilbert has found a hair in my soup which spoiled everything. Einstein pulled out the dive just in time. By late 1915, he knew that the influential German mathematician was close to finalizing a theory of general relativity himself. In a few feverish weeks in November, Einstein reverted to the equations of general relativity he had in hand for more than 2 years and applied the finishing touches. In November 1915, in the first of 4 lectures before the Prussian Academy of Sciences, he announced his achievement. Our view of the physical world has not been same since then. Einstein initially wanted his equations to be coordinate independent, a property which is called general covariance, meaning that they would produce correct, consistent descriptions of the universe regardless of which coordinate system you happen to be using. But Einstein convinced himself that in order to fix the error he thought he had made, he had to abandon general covariance. The Einstein field equations we have today are generally covariant. They express the same physical truths about the universe, how space-time curves in the presence of energy and matter, regardless of what coordinates you use to label things. Perhaps the man who made Einstein famous was none other than Sir Arthur Eddington. By the time Einstein was a well-known scientist, but his leap to immortality began to take shape when he was working on the generalization of relativity to gravitational fields to build a theory of gravity that modified that of Newton. Apart from his epoch-making experiment, Eddington is also known for Eddington experiment, Eddington limit, and Eddington number. English astronomer, physicist and mathematician Arthur Eddington was fortunate in being one of the few astronomers with the mathematical skills to understand complex theory like general relativity. He and astronomer Royal Frank Watson Dyson organized 2 expeditions to observe a solar eclipse in 1919 to make the first empirical test in Einstein's theory, the measurement of the detection of light bent by the sun's gravitational field. Eddington dedicated himself to promote and publicize Einstein's work among his colleagues. However, he was not satisfied with just this. The astronomer was also determined to test the prediction about the curvature of light. As lifelong Quaker, Quaker means a religion society who believes of God in everyone, Eddington abhorred the war and saw the eclipse expedition in which British astronomers would test the theory of a German-born scientist. The results were presented in an atmosphere of great expectation at a joint meeting of the Royal Society and the Royal Astronomical Society held in November 6 of that year. The verdict was unequivocal. Einstein was right. But the implications of that discovery reached infinitely beyond an interesting astronomical phenomenon. The verification of a consequence of general relativity meant validating Einstein's theory of gravity, overthrowing the Newtonian model that had remained in force for more than 230 years and unveiling the enigma of action at a distance. According to Einstein, the universe is formed by a fabric of space-time that is distorted by the mass of bodies, and this distortion also bends light. Karl Schwarzschild, born on the 9th of October 1873 in Frankfurt to his Jewish parents. He was the first to provide the first exact solution to the Einstein's field equations of general relativity, but for a limited case of a single spherical non-rotating mass. From 1901 until 1909, he was a professor at the prestigious Institute of Göttingen, where he had opportunity to work with some significant figures including David Hilbert and Hermann Minkowski. At the outbreak of the First World War in 1914, he joined the German army despite being over 40 years old. He served on both Western and Eastern fronts, rising to the rank of a lieutenant in the artillery. Einstein never spent a great deal of time looking for an exact solution. The part that described gravity around matter was extremely complicated because gravity distorts the geometry of space-time, causing particles to move. Approximate solutions could describe with sufficient accuracy phenomena such as the bending of light. Nevertheless, he was impressed when in 1916 German astronomer Karl Schwarzschild came up with an exact solution for a realistic situation, in particular the case of a planet orbiting around a star. In the process, Schwarzschild found something disturbing. There is a distance from the center of the star at which mathematics goes weird. At this distance, now called the Schwarzschildradius, time vanishes. Space becomes infinite. The equation becomes what mathematicians called singularity. The Schwarzschild radius is usually much smaller than the radius of the object. For the Sun, for example, it is 3 kilometers, whereas for a 1 gram marble, it is 1028 centimeter. Schwarzschild was of course aware that his formula went crazy at that radius, but he decided that it didn't matter. He constructed a simplified model of a star and showed that it would take an infinite gradient of pressure to compress it to his radius. The finding, he argued, served no practical interest. But his analysis did not appease everybody. It bothered Einstein because Schwarzschild's model star did not satisfy certain technical requirements of relativity. He first set down in a letter to Einstein on 22nd December, writing while Schwarzschild was serving in the war stationed at the Russian front. Schwarzschild concluded the letter by writing, "As you see, the war treated me kindly enough in spite of the heavy gunfire, to allow me to get away from it all and take this walk into the land of your ideas." In 1916, Einstein wrote to Schwarzschild on this result: "I have read your paper with the utmost interest. I had not expected that one could formulate the exact solution of the problem in such a simple way. I liked very much your mathematical treatment of the subject. Next Thursday I shall present the work to the Academy with a few words of explanation." Christoffel was born on the 10th of November 1829 in Prussia in a family of cloth merchants. He was initially educated at home in languages and mathematics. Bruno Christoffel was a German mathematician and physicist, known for his contributions in differential geometry, Christoffel symbols, and Riemann-Christoffel symbols. He introduced the fundamental concept of differential geometry, opening the way for the development of tensorcalculus, which would later provide the mathematical basis for general relativity. Christoffel was interested in the theory of invariance. He wrote 6 papers on this topic. He wrote important papers which contributed to the development of the tensor calculus of Riccicurbastro and Tulio Levi Civita. This gamma term acts as a connection coefficient of the Levi-Civita symbol. Ordinary derivative from one frame of reference does not transform, keeping things intact. So for that, what we need? Christoffel symbol. A correction term, a compensation, so that the ordinary derivative of a tensor can transform from one frame of reference to another. The Christoffel symbols which he introduced are a fundamental in the study of tensor analysis. Christoffel is mainly remembered for his seminal contribution to differential geometry. In a famous 1869 paper, he introduced the fundamental technique later called covariant differentiation and used to define the Riemann-Christoffel tensor. Christoffel's ideas were generalized and greatly developed by Riccicurbastro and his student Tulio Levi Civita, who turned them into the concept of tensors and the absolute differential calculus. He was a close friend of Albert Einstein. During his years at the Federal Polytechnic Institute in Zurich and then at the patent office in Bern, where he helped Einstein get a job. Einstein called Beso the best sounding board in Europe for scientific ideas. In Einstein's original paper of special relativity, he ended the paper stating, "In conclusion, let me note that my friend and colleague M. Beso steadfastly stood by me in my work on the problem here discussed, and that I am indebted to him for many a valuable suggestion." Michel Beso and Einstein first met as students in Zurich in the late 1890s, and their friendship was cemented during their time working together in the early 1900s in the Swiss Federal Patent Office in Bern. In the evenings after work, the two friends would stroll home together, and many years later, Einstein would remember how thoughts of everyday life would fall away as they discussed scientific subjects. When Einstein changed the world of physics forever in 1905 with 4 groundbreaking papers, Michel Beso was only his acknowledged collaborator. This is a letter showing Einstein's emotional moment which he wrote to his friend during his Eureka moments. Einstein told Beso he was desperate to reconcile two opposing ideas. It had long been proved that the speed of light was constant. So how could the distance that the light travels change depending on whether the sailor or the person on the shore sees it? Beso and Einstein debated and prodded at the question as they walked along. How could the speed of light be constant, yet the distance of light traveled be relative? Round and round and round they went, but got no close answer. Eventually Einstein grew tired, announced he was giving up, and parted for home. In that moment, Einstein's groundbreaking theory of special relativity was born. When he met again with Beso the next morning, Einstein said, "Thank you, I have completely solved the problem." 6 weeks and many more discussions later, Einstein published his new theory with his acknowledgement to Beso. Einstein and Beso remained best friends for life. A testament to the power of close, supportive relationships to bring out the best in our colleagues. He could only converse and talk with Beso about the key scientific concepts of his career and far more ahead. George Friedrich Bernhard Riemann. Riemann was a bashful and impoverished German mathematician known for his famous Riemann hypothesis, one of the unsolved Millennium Prize problem. It was Riemannian geometry that enabled Einstein to establish the bridge between light, matter and space-time and translate his uncanny intuitions to the theory of relativity. Riemann, as we called him the granddaddy, is known for his Riemannian geometry, Riemannian tensor, Riemannian manifold, Riemann zeta function and Riemann integral. All of them are the key players or the key concepts in Einstein's field equations. As we will see, we will start with Riemannian tensor, and that is why we call them the granddaddy, because from him everything starts. Riemann's teacher at Göttingen was Carl Friedrich Gauss. In 1854, Riemann's lecture on the hypothesis which lie at the foundations of geometry founded the field of Riemannian geometry. In this lecture, Riemann introduced the concept of metric tensor, which is a key to understand general relativity, geodesics, which is another important factor which we will learn, and curvature tensor, now called Riemann curvature tensor. Each of them played a pivotal role in Einstein's general relativity. Gauss was present when Riemann delivered his lecture. He expressed both astonishment and excitement to his friend Weber about the depth of Riemann's new ideas. In 1915, Einstein's publication of relativity theory exploded worldwide interest in Riemann's geometry. Einstein told, the genius of Riemann, solitary and not understood, had already casted its way in middle of the last century to a new conception of space in which space was deprived of its rigidity and the possibility of its participation in physical events was recognized. As you can see, all these people and more contributed in Einstein's development of his ideas, mathematical and geometrical formulations of general theory of relativity. Whether be it Marcel Grossman, Tulio, Levi, Civita, Arthur Eddington, Gregorio, Riccicurbastro, David Hilbert, Riemann, or his friend Michel Beso, Karl Schwarzschild, who first provided the exact solution to Einstein's field equations, or Elwin, Bruno, Christoffel. All these 9 luminaries and more contributed, without which it was not possible for Einstein to develop the general theory of relativity. I hope you liked my video. It was a kind of a historical account, but nevertheless it is important because we need to understand the base on which Einstein developed his general theory of relativity. This is my channel, youtube.com/physicsforstudents. Don't forget to subscribe, like and press the bell icon so that you can keep on getting updates about mathematics and science, particularly in this video, which is very extensive on Einstein's field equations. My next video would be on what is a field equation, in which I will be describing what is a field equation, and further we will be taking steps step by step forward into the intricacies and component analysis, mathematical, and in a simple way understanding what is Einstein's field equation and how important it is. I am thankful that you have been with me for such a long time, making my channel grow. I would request everyone to subscribe, like, and please do put up your comments because comments are very important. Thank you very much, and thank you for watching my video, and have a nice day ahead. Thank you very much.